as a corresponding PV diagram for it as well. So a gamma type Stirling engine has two piston cylinders. It has the displacer piston and the power piston. So from process 1 to 2 in the gamma type Stirling engine, we have isothermal heat addition. And in order to maintain that isothermal property, we have to have the piston expand. So that's what we see here going on. The piston is expanding in the displacer. Next, we have a constant volume process from 2 to 3. And for the gamma type Stirling engine, each piston is connected to the same crankshaft or flywheel, depending on the design you choose. And they are most common 90 degrees out of phase with one another. So that is what allows these two piston cylinders to move at the same time, allowing for that constant volume process. So moving on to state 3 to 4, we now have a constant temperature or isothermal heat rejection process, where heat is leaving the cold reservoir, and now we have the constant temperature, so we have the compression of our power piston. And then similarly, we have another volumetric, isovolumetric phase where both of the pistons are compressing. So that kind of sums up what exactly is happening with the gamma type Stirling engine. The regeneration process is between the hot and cold reservoirs in the displacer piston as well. We've also researched many other different types of hot air engines, such as the Ericsson engine and the Atkinson engine. The Ericsson engine is typically for much bigger applications. They usually use them with coal, for example, and they're much bigger, clunkier. They also have valves that are opening and them a very complicated process. The Atkinson engine is very similar to an Otto cycle. However, the only difference between the Atkinson cycle and the Otto cycle is that the Atkinson cycle has a exhaust valve that actually remains open for a slight period of time during the compression process. However, this is an internal combustion engine. So, for example, the Atkinson engine is something that we decided not to go with for our project. We've also researched the different types of Stirling engines. So as you can imagine, the gamma type is not the only one that we have. There is also an alpha type Stirling engine in which the hot reservoir is connected directly to the connecting tube. This engine has a lot of dead space in it, so we decided not to go with it. And finally, we also have the beta type Stirling engine, which is actually very similar to the gamma type, as you can see here. However, the only difference is that the beta type actually has only one cylinder as opposed to two. So both pistons are in the same cylinder for the beta type, and this actually creates a lower power density. And not to mention, it is much more complicated to build as well. So all in all, we decided to go with the gamma type Stirling engine.
So as we were doing all this research, we decided it would be really helpful to have a physical model so we can visualize what the heck's going on. So we got that guy there off Amazon, and it's a lot of fun to play with, but it was also very useful in our design process. One, we found various problems that could occur with the Stirling engine, which will be touched on later. But two, we dove in and we started reverse engineering it. So we started taking it apart. We took note of all the tolerances and fits that were involved and how all the parts interact with each other, which was very interesting to do. We also took note of the process of disassembling it and how that works. After we disassembled it, we put it back together, and we took note on all the steps involved in putting it back together. And overall, it really helped us understand how the Stirling engine works and how all the components interact with each other. Here's a video of it running. It looks like it's moving really slow, but it's actually moving really fast. But it's pretty cool to see.
Yeah, if you guys want, we can run it for you after the presentation.
So then we dove into the analysis, and at the beginning, we did not know where to start until we found Mr. William Beale. Mr. William Beale, and for those of you who don't know, he did extensive research on Stirling engines, and he came up with a formula that relates the volume and the bore of the power piston to the thermal reservoir temperatures. So this is a perfect starting place for us, and we used his equation and got a volume and bore. Then with the volume of bore, we decided to go the thermodynamics route where we wanted to find pressure. And we made some assumptions here that it was going to be an ideal Stirling cycle. The air was going to be modeled as an ideal gas, and everything was going to be running at steady state. So with these assumptions, we were able to find the pressure in the power piston cylinder. We converted this pressure to a force because we knew the bore. With that force, we designed the piston itself and then moved on to the connecting rod. For the connecting rod, we needed to do some kinematic analysis in order to accurately predict the force that's involved. So we did a kinematic analysis. We assumed constant angular velocity of the flywheel to simplify things. And we were able to find acceleration and velocity at both ends of the crankshaft, which were used to find the force in the connecting rod. Once we had the force in the connecting rod, then we went and determined the yield strength that or the material we wanted to use, and then compared it to the yield strength. Got a preliminary design from that. Then we went and looked at fatigue strength and found that it did fail with the Goodman criteria. So we modified it to be a little bit bigger. And then after that, we had our initial design for the linkage and we moved on to the flywheel. So our first thoughts was to do a dynamic analysis and do a torque balance on the flywheel. But the problem was we didn't have the force from the other side of the engine, the displacer side. And that's what we're currently working on now, is getting the fork from that side, which is a little bit more complicated than the power piston side because there's a gap. It kind of floats in there rather than a normal piston cylinder. It's tied up against the walls, which simplifies things. So that is where we're at with our analysis and our design.
So one of the things, as Jay said earlier, was we were running into an issue when we were running this Stirling engine right here. We were realizing that we were breaking the maintenance criteria or constraint because every time you would light the candle and let it run, it would build up soot, and it's technically a maintenance issue. So we had to look at, well, what can we do to decrease the amount of soot? And I'll pass it off to Ashley to talk about that.
Yeah, so what we did is basically we developed a procedure and we documented different types of fuels and like the length of the wick and stuff. So we use different lengths of wick, like longer, shorter, and how close the bulb is to it or not. And we developed a procedure that would show us like how much soot would be developed on the bulb. And as you can see, by just changing the fuel, you can see how much better it got from the first slide. But while we were originally using isopropyl alcohol, you can still see the issue on there. And that's after running for about a minute. And this would usually be ran for about up to like 10 minutes at a time. So that becomes an issue. So we ran them all and we compared the soot production, and we found that actually the denatured alcohol produces the least amount of soot. And although it's kind of hard to tell between those two pictures, there is actually some on the methanol picture there. And then while we were also at all of this, we decided we'd run some other tests on like how long is the run time just for like the enclosure we have here, as well as what's the startup time. And where the startup time is like when you light it, how long it takes it to like start actually moving. And we found that just across the board, denatured alcohol was the best option. So that's what we went for with our fuel selection, to completely reduce the maintenance.
And so currently we have a SolidWorks model. It is, but it is just of the power piston. Here's an animation of how it's working. And then looking forward into next semester, the 3 bullet points on the left-hand side are progress. So we plan to finish those up, the displacer piston, finishing up the flywheel, and we do have a current CFD analysis for the effective cooling fins. And so we also plan to look at the stress analysis of the frame itself, and also looking into different instrumentation, sensors, looking more into depth according to standards, specifying the build materials, getting prototype build. And we do have a polyimide heater on the left picture, and we do have our TD sensor on right, and the display at the top.
Right, so thanks for coming to our presentation. We'd just like to thank all the people that helped us with our, like, push us in the right direction for our analysis, as well as the people at Plexus for giving us some guidance in funding as well. So here are some of our sources for some of our stuff, and we'd like to open it up for questions now.
How much was the Sterling engine that you got from Amazon? Could you make the argument it meets your constraints?
I mean, yeah,
Some of them.
Sure. So this is really gonna be my question was, what is your design going to do that, say, an existing Sterling engine that you can get off the shelf doesn't do?
well, especially the display. We don't have a display, and I know you could probably say, oh, you could just hook up a display to this guy. But we couldn't do that because one of our main constraints is that we need to manufacture at least 75% of our parts. So we can't just pull one of these guys off the shelf and, you know, throw some sensors on it in a display.
So that was a customer requirement?
Yeah.
Okay. So my question is a little bit related to that, but since this is going to be a laboratory piece of equipment, what are you measuring? What are the design inputs in terms of measurement?
I think so. We're going to be measuring the thermal reservoir temperatures and then calculating efficiency, and also power output, how much it's generating. So those are the main ones.
I believe power input is also one of the things that we'll be measuring. It was only specified that we needed to measure that for the electrical input.
Okay, because that was going to be one of my questions, is how do you get input if you're burning denatured alcohol?
Yeah.
One of the reasons I asked that question is that your measurements cannot be separated from the design of the device itself. I mean, these need to be integrated. You can't design, well, now we got the engine, oh gosh, now how are we going to instrument it? Right, because you end up with some hand-handed stuff. So what you want to do is integrate that measurement directly into the design of it, which gets to Professor Dayswater's point, which is, why don't you just get an off-the-shelf thing? This is not an off-the-shelf application. And so you have to think about how this particular application impacts your design. And again, it's a laboratory piece of equipment, so it's student interaction, it's measurement. And keep those in mind as you're designing the sort of mechanical parts of it.
This one might be just a little basic, but can you run these in a general classroom, or do you need to be in one of the test cells downstairs, the lab?
Well, for
That's-
safety, yeah, we
Yeah,
were,
it's something we're still gonna look into. We're planning on looking into rules, along with like codes and standards for like, you know, how to make it safe enough to be allowed in the classroom. But we haven't gotten to that.
I mean, honestly, it's not like it's super unsafe. It's pretty much probably about the dangerousness of, like, you know, just like a tea light, you know, give or take, because, you know, there is like liquid fuel in there, but it's safe enough to run, but it's we're not entirely sure what the, you know, full breadth of that deal is.
Upon the completion of the engine as well, we do plan on having an operating manual so that whoever is operating, whether it be a teacher or a student, they know how to properly and safely operate the engine.
So do you anticipate that students might be using this without supervision?
Generally not,
Probably not.
no.
Yeah.
I mean, leaving college students alone with an open flame, you know.
It could be bad news.
Could you go back to the schematic of the Gamma Sterling engine?
Sure.
So there are two phases where the power piston is moving, but the displacer piston is not moving, right? And then the other two phases where they're both moving in concert to keep it as an isochoric process, right? So is that something that you talked about? How do you sort of engage them and then disengage them? Does that kind of make sense? Because you said that they were going to be connected through like a flywheel so that they're moving in concert, but they're obviously not going to be moving in concert during the isothermal processes, right?
Yes, so part of that has to do with the phase angle that they are operating out against. For example, looking at this engine, you can see that one of them is 90 degrees out of phase with the other, allowing them to move at, I guess, at different times. So that's what's going to allow for one to move at one time versus two to move at one time.
So there's going to be two separate flywheels then?
No, there's going to be one flywheel, but they're connected at different points on the flywheel.
Oh, okay,
It's a
okay.
little hard
Right,
to imagine.
actually
but-
get
We could bring it over.
It's just when one is at its maximum velocity, the other one is stopped.
Got it. Okay, okay.
But they're technically both moving the whole time.
We'd like to welcome anybody to come take a look at the model that we've been using for our reverse engineering, to come like see, I guess, that 90 degrees phase angle as well, because it's kind of hard to see on one end and on the back side as well.
And then I just have one quick question. Can you go back to, was it your Gantt chart maybe? Yeah. So are you gonna put in a patent application for this then?
No,
Oh, okay.
We were following Almond's process.
Oh, so this all the stuff under like his process?
Yeah.
Okay, okay.
at the beginning of the year when we were making the Gantt chart, if that's something that we were going to consider, we did a lot of time for it.
Got it.
But we've pretty much decided that's not something that we're going to do. That we selected in the Gantt chart is.
Yeah, sure. I'm just curious.
But if no other questions, round of applause. I'm trying right away, if you get done on TV, but if you would rather like spend time, we have. time.
Okay, I got it.
That's fine. Yeah, absolutely. Thank you for so. That is very much. Thank you.
Oh, Dr. Bios, I forgot to mention this, but the camera itself is very tight window
Yes.
and we can capture, it's essentially a person's weight, so away from the projector screen.
Yeah, I mean, that's what I see here, which is like, it's capturing the screen and not the people. And that's what, I mean, that's what Dr. Hart set it up and I'm just like leaving it be.
No, I just noted that a couple of the presenters just now were on the outsides. of the-
Yeah, that tends to happen a lot.
But I mean, I don't want to mess with the camera because it's
No,
anything.
don't
like-
mess with the
Yeah.
camera. It's just, what Hart was doing was encouraging people to move towards the.
All right,
screen,
I'll
especially
remind
this
people
way,
to kind of be closer, okay, that's
because
fine,
otherwise you hear a voice and you don't.
sure, okay.
It's a ghost.
Yeah.
Goes on.
I just want to make sure I'm not obstructing the view of the camera, am I?
I'm sorry,
I'm not obstructing the view of the camera sitting here, am I?
no, you're not.
Okay. She's still there?
Oh, no, she's been here.
Probably still is.
Yeah,
you can see it now. Like, hello, see my grandma's still there.
I'm just gonna take it back with you.
So we're going to wait until Dr. Reed comes about.
Yeah,
And then we
absolutely.
get started.
Yeah, we got time.
The only thing is it has like hell of a vibration, so it moves around, so we're gonna actually. Yeah.
It's actually pretty
Have you done-
great sounds.
Have you done a vibration analysis?
Yeah.
There wasn't really a specification as to how long the wick should be.
Yeah.
So we decided to like that.
Yeah.
Yeah, I'll probably have that in the manual as well.
Yeah.
Obviously, it won't be used perfectly every time, so that's why we also changed the fuel, you know. It's like it though, isn't it? It's just like, you know.
Like, that's what I used to do.
Yeah, we can have something.
You said there was treasure.
Yeah.
Yeah,
so
like,
it's
when
like.
it's, you're not gonna- it moves around.
Yeah.
No, that's fine, that's good.
So.
All right, so next team is going to be Pentonville Energy Conversion Unit. Let's get started.
Hi, our project is the Pelton Energy Conversion Unit. Here's the team. Our client is MSOE. Our advisor is Dr. Bias.
And I'm Max Stewart.
Relations, and I'm Rachel Brock. So a little bit about the project. MSOE has requested that we build a Pelton conversion unit, so students can implement that in later labs and be able to visualize the water jet velocities, kinetic energy being put into electrical energy. Displays will be jet velocity, flow rate, current and voltage, and this will allow the students to be able to calculate the efficiency of the unit as well as the power output.
To start off, we followed the 5-phase design process by element. The first stage being the project definition. The stage first included conducting background research and patent research, and then creating a schedule to follow for the rest of the project. So to start off, we're just gonna cover some background on the fluids of a Pelton wheel. The generic Pelton wheel just consists of a rotor that has buckets mounted to the rotor. And then a nozzle projects a jet of water that strikes the buckets as seen here. The water changes direction, and then this change in momentum imparts a force on the bucket, which creates a torque on the rotor, which would be used to produce power. Here is just where I'm finding the momentum balance, and then if you factor in the radius of the wheel and then the rotational speed of the wheel, you can get a power produced. And then by looking at the relationship between the jet velocity and the rotational speed of the wheel, we can see that when the jet velocity is twice the speed of the bucket velocity, actually the power output is maximized. So this is what we should strive for in our design process. Here we did some patent and literature research. This was done an article where they did CFD analysis for multiple wheels that had different amounts of buckets and different nozzle setups. And the general findings were that having additional buckets will slightly increase the efficiency, but it's a pretty small amount. And then that the surface roughness of the buckets has a large factor in that. We also found that having additional nozzles can also improve the efficiency slightly, but the nozzle diameter plays a greater role in that, with a smaller diameter giving greater jet velocities, which can lead to higher efficiencies. Here was our Gantt chart. As you can see, it followed the design process with the different stages being outlined here. I had general deadlines set for the earlier stages of the process where we knew general event outlines, but the later stages are left open for the following term where we can then lock those in later.
Okay, the next step in the design process is the product definition. This includes requiring and understanding the constraints and the design objectives, as well as setting targets for our group internally and evaluating competition. So some of the constraints is it needs to be safe for the instructors and the technicians using it. It has to fit in the SGO1 tank, the green tank, as well as it can't damage the tank in any way. It needs to be 50% of non-metal material. It needs to be maintenance every 25 uses or every 4 months, whatever comes first. And it has to be less than 5 kilograms. And then there's our design objectives. It will convert at least 50% of the kinetic energy into electrical energy. It will display jet velocity, flow rate, current, and voltage. We will have to have means to control the rotation, for example, a brake, It will be efficient and every run, it'll be within the 5% efficiency of the last run. As well as it will be enclosed into the tank, so no one will get splashed during the trials. And it should be easily viewable so the students can learn and visualize what is going on within the wheel. And then as a group, we collectively decided on some targets. We don't want to exceed $500. We don't want the noise to be 70 decibels or less. We want to make 3 changes at the end to make it more aesthetically pleasing. We want it to be easily disassembled for storage purposes. And we also want the components to be able to be easily replaced when anything breaks. So in order to kind of get a grasp on which of the constraints and the design objectives are the most important, we did a QFD, which is a quality function deployment chart. We scaled everything up to 100, and we talked with our customer, which was Dr. Baez, on which of the constraints are the most important. For example, it has to fit in the SGO1 tank. The tank won't change sizes. We can't have it damage the tank in any way. It's not our property. So that was a big one. As well as safety, we have students using this. We don't want anyone to get injured during the runs. And as well as the energy should be 50% of the kinetic energy to the electrical energy. So with those key points, we ranked those higher than the other ones. And then we were able to compare that to 3 competitors. We had one from Sunlab Tech, Hamburg, and Edidon. These were all small display units. So it was comparable to ours. Most energy conversions are large scale, so it's difficult to find a smaller scale. But we were able to do that. And with that, we were able to see which ones lined up with what, which ones weren't. The Hamburg was the best for the 4 main constraints that Dr. Baez and us agreed on. But it was allowed us to see what to focus on more for our decision matrix, for our morphology chart, and things to really focus on in the future. Here is just our ranking, how we ranked everything from 1 to 5. I'll do one example. It was the hazard safety. So we ranked that based on possible areas for hazard. So 1 would be there's 5 possible ways someone could get injured. 1 would be there's none. For example, if the electrical wires are too close to the water, the buckets are exposed, you could jam your fingers. And we did that for each constraint in the QFD. The next thing we did was evaluate competitors. We bought a small wheel off Amazon from Alesco. We did this for 2 main reasons. 1 was to reverse engineer it, look at the design, see what we liked, see what we didn't like. It was also to run preliminary calculations. In the design process, we realized we liked the motor pulley system, how it was directly connected to the shaft, which was directly connected to the wheel. However, the buckets inside were small single buckets, and with our research in the patents and research papers, it was clear that dual buckets in a more oval shape are better for the efficiency. So that was something we saw and we didn't like. Then we did our initial calculations. We hooked it up to a pipe in SGO1, and then we were able to calculate the mass flow rate by timing the water going into a bucket and then finding the mass of the bucket. And then we found the volume flow rate by finding the density of water. And then with the jet nozzle, we calculated the diameter using calipers, and that was able to get us the jet velocity. Current voltage with the multimeter was able to get us the power, and then we were able to see the kinetic energy and the efficiency. As you can see, this display model is not really comparable to what we need to be doing. It had an efficiency of 0.001. And the electrical input and output were very low. So we learned during this process that this is not something we could model our stuff after. However, it was important for us to be able to realize what calculations we need to be doing, how to make things a little better, different sensors, and a different way of solving everything. So that was important for later processes.
So the next phase in the 5-phase design is conceptual design. And so going through this, the steps are generating concepts, evaluating concepts, making decisions on those concepts, and then can be an iterative process going back to refine those concepts. And then after that, move on to documentation and communicating those concepts, refining the plan, and then either approving or going back and going through the process all over again. So the first thing we did was a morphology chart. We went over and came up with the different functions that our Peloton wheel needed to be able to perform, and then came up with different ideas for how to possibly perform those. For some of these, they were a little out there, or something that we knew probably we weren't going to do, but we just were focused on generating ideas in this step. So then we came up with 3 initial designs, which you can see here. The first design A here would sit on top of the tank. You can see it is completely enclosed by clear plexiglass aside from the drain and the inlet for the jet. It features 2 separate compartments, one where the wheel and water would be, and one where the motor and all the electronics would be to keep those dry. It also features a driving water jet coming in from the side and a brake jet coming in from the top. Moving on to design B, that would clip over the sides of the tank. It only had a driving nozzle and no means of braking. The motor, generator, and hex shaft in the center, which connect to the wheel, were connected by a pulley, and it was not fully contained, but had a splash guard on the sides and top to prevent splashing. Then design C, as you can see here, also sat on top of the tank, and it was completely enclosed with an enclosure which would house the wheel with the buckets, an inlet for the jet, and then a drain. And then the pulley that would connect to the generator is outside, and all the electronics would be separate from the water.
For all of these designs, we were planning on using 3D printing to produce the bucket. I was excited to do some testing to make sure that we could run ahead with that idea. And so we came up with just a generic model in CAD for a helping wheel bucket and printed it off, and it turned out to be a success. The shape held well and the surface was rather smooth, so we decided that this was a feasible idea, and then we can move ahead with that for planning.
So once we had confirmed that we'd be able to 3D print the buckets, we went through and came up with a decision matrix to evaluate the different designs we had. Which you can see, this was our ranking system. We had the different criteria, and then we ranked them different, with a scale of 0 being the worst and 5 being the best. And tried to have qualitative. Yeah, so then here's the design. Is A, B, and C, and then a modified design B that I'll explain in a minute. They were weighted. The weights were based on the QFD and our customer requirements, and they all this added up to 1. So the design B did the best with a score of 3.8, then design A with a score of 3.74, and then design C with a score of 3.28. However, when we were looking at design B, you can see that in brake performance, it got a 0, whereas design A scored a 3. So design B didn't have any means of braking. So we ended up adjusting design B, including the brake nozzle from design A, and we ended up with a modified design B, which had a score of 4.13 out of 5, and that was the design we selected to go with. So here you can see that design, a 3D CAD model of it in the tank. In SGO1, there's on the outsides, there's the Arduino battery pack, the 3 displays for displaying the parameters we'll be measuring, generator on top, clear plexiglass splash guard, frames here, which have inside between the metal and the tank, a rubber grip to help keep the design in place as well as control vibration. And then you can see there's a driving nozzle and an orange braking nozzle. And those would be connected to the existing tubing in SGO, or piping in SGO1 using flexible tubing. And here we have an animation showing how everything would fit together.
Okay, and then we did an estimated budget. I'll point out some key points that was specific to our design. We are doing flexible tubing for the drainage tube and the jet tube. Then we are going to use 3 main sensors, a flow sensor, a voltage sensor, and a current sensor. We decided to use a hex shaft, so we don't need a key. And with that said, we are going to decide to 3D print the wheel, custom fitting it to the hex shaft, and then also 3D printing the dual buckets, which will be the rounded shape that was shown previous in the prototyping. As well as, we bought the customer product on Amazon for $123. Our constraint, our target was 500. So if that was not purchased, we would have been under our budget. However, we've been allocated $750. So we have an extra $200 with this design process in case any errors occur, as well as anything needs to be adjusted. So we're planning for the worst case scenario, which is a safe bet. So step 4 is product development. We have not reached step 4 yet. We reached step 3, which is the conceptual design. This will be started next term. That is manufacturing, building, testing, cost analysis, finding our plan, seeing what's going wrong, and then getting the whole concept put together. So for next term, before we start building, we're gonna do some combined loading equations, an FEA analysis, we're gonna order our parts, and then do a CFD analysis. After building, we're gonna refer back to the QFD, the constraints, the targets, and the design objectives to make sure everything we have so far is fitting those as needed. And then we're gonna run our calculations based off of our evaluating our competition to make sure that the 50% of kinetic energy is put into electrical energy, as well as the efficiency is at the scale that we need it to be, and everything else runs as normal. Then the 5th step is the product support. This step is going back to your customer saying, hey, do you like this? What's going on? Is anything need to be changed? As well as for us to see, okay, what needs to be tweaked to make this run better. So then this is a rough timeline for the next semester. Over Christmas break, we are going to order the essential parts that we know will not change. So the sensors, the vibration, the rubber pads to help vibration. That was a key part of our design that we are going to stay with, the hex shaft, the flexible tubing, and then we were going to start 3D printing as soon as we get done with all the ordering the parts. And then week 1 through 3, we are going to do all of our analysis to make sure our design is structurally sound and it will work how we need it to. So we're going to do combined loading equations, FEA analysis, and fluid analysis, as well as some CFD. Each of us are going to be in charge of our like strong kind of suits that was discussed in the beginning of the semester. Then week 4 through 6, we're going to do preliminary building. So that's going to be our Arduino setup, our 3D printing, and then overall looking at the design, seeing if anything needs to be modified before we start building fully. The 3D printing and the Arduino setup is important to start before because we haven't done a ton of research and we haven't fully started the 3D printing. So we wanted to make sure all that's secured, set up, and then we could build the rest of our design and everything could flow smoothly after that. Week 6 through 8, we're going to try to get everything built, have our final design by the end of week 8, giving us plenty of time to fix anything because things go always slower than you think it will. And we want to make sure we budget at that time. And then 8 through 16 is going to be our testing for the flow rate, for the energy, for the efficiency, and then rebuild and adjust and make sure that we are really talking closely to our customer and make sure it's applicable for a lab and it's not just in our brain. We can run it easily. Students who've never seen this before can understand how to work it, and it's like fully thought out. So when we're done, week 16, it can be implemented into a lab. Thank you for your time. This is just a quick schematic of our SolidWorks and our final design, as well as some weights and other calculations that show that it's falling into the constraints. It's at 46 kilograms, our constraints 50. So we're right on level with that. Thank you.
The efficiency was really that low on.
Yeah.
The design we purchased was made to be run in like a kitchen sink. So it was way undersized for the amount of fluid that and water we were getting from the flow bench.
The motor was also scaled to just like light up a single LED or like another small motor, so it's not being used, so.
Yeah, so it was also in addition to the buckets not being designed well,
Sure.
it was just
Tiny.
way under.
It was also
under
tiny, it's
scale.
like the size of our hand. Fully, so,
So in other words, you are running far larger floor rates than what it was designed for?
Yes, yeah,
it was also interesting because we set it to what they said. So like said it, they were like, oh, like on the reviews, it was like, says they're running my kitchen sink, but like the wheels aren't turning. And then we tried initially to run it in the SGO1 sink. And if that's what you want to do, not at that rate, because it did not move at all. And then we upped the jet velocity and it started moving, the light turned on, the wheel was spinning. So it was definitely like generating power. But during this entire process, water was spilling everywhere.
Sure.
It was all near the electrical, so it's definitely not a product that's comparable to what we need to build.
It's wild. How are you guys gonna handle the fluctuation of flow from the city?
Insane. A great question.
Well, I think there's some like control settings that you can, it'll be hooked up to the flow bench and the fluids lab, so we'll have some control over it there. And then for us, when we were testing the competitor project, we were looking at an average over a course of time. So if we're noticing when we're running it that it's fluctuating too much over a short period of time, we'll like advise students to take averages over a certain period of time and use that data instead.
You looked at the flow bench before, so that is all gonna be in the flow bench in the west.
Yes.
yeah.
Yeah, in that,
That-
yeah, that green tank right by the floor
But on
bench.
scale.
Oh, that's, okay. That's a really good question. As someone who's been working more than 30 years in that lab, the fluctuation in flow water pressure is significant. That's why there's an accumulator on it. You should see what it was like before I had the accumulator installed. It would be like that. Every time people would flush toilets in the building. So this is going to be a serious issue. So I'm not sure averaging is going to get you where you need to go. But I think I think you're going to have to look at how do we get a consistent flow rate.
Absolutely.
If you're just using city water. You have some sort of so this gets to another question I have, which is, what are the actual expectations? Maybe I didn't see them. Specific numerical, how much power out are you looking for?
The only
It's
constraint,
efficiency rather than like a power out.
Okay, but I'd like to know, do you anticipate a power out? Are we talking about a tenth of a watt? Are we talking about 5 kilowatts? Are we talking about? What are we talking about?
That's something we're still working on figuring out. That's we're in the process of some of those calculations and figuring out. That'll be in the next step.
Okay.
Along with the structural loading.
Okay, but you have a general sense of the size of the thing, so you must have some idea of.
right now, we have it planned to have a motor that goes up to 12 volts, like 400 RPM. So then we're debating on if we need to up or limit that based on the velocity we're going to use or the control of that. So we haven't thought it fully based on what motor and generator we need to produce a certain power, since we don't know what it's going to be able to handle at this point.
Is it motor or generator?
Generator as of now.
I mean, motor that,
Yeah.
you're generating electrical power.
Yeah, and then our other plan is we can adjust like the size of the nozzle we're using if to control the kinetic energy of the incoming jet.
Okay, do you have any round numbers or raw numbers on the kinetic energy? That is, what kind of flow are we talking about?
We do not as of this point right now. That is something we'll be working on.
Okay. Because I'm trying to get a sense for, is it, the hole is this big, is it this big? I mean, what are, what kind of velocities are we talking about? I'm not getting a sense for numbers there.
We're trying to limit the size of the velocity jet as small as we can. So right now we have a 7/8 diameter.
Okay,
Um,
there's a number.
yes, so that's the plan as of now. However, we do not know what that's going to produce. So the next step into CFD and FEA and like trying to run and simulate the water jet velocity and try to set a number, see with that nozzle what number we're producing and seeing if we can actually replicate that in the lab. And if we can't, then we're gonna go back on our design, see what diameter we need, how many buckets, and if that works. And if not, we'll up the size or lower the size. But as of now, we think the 7/8 will fit and do the job.
So this sort of like piggybacking off on Professor Swedish's question, which is, because I always wonder about this, which is, what are you hoping to get from the CFD analysis?
We're looking at just getting some what we started with for CFD was the force on a stationary bucket. So if the brake, if for example the brake and nozzle were engaged at the same time, and from changing comparing the bucket size and like the diameter of the jet, and also possibly changing some of the geometry to see how that changes. We'll also be doing some calculations based on equations from the research we found as well to make sure we're validating and verifying the CFD.
Sure, good. The only reason I was asking was, I gotta imagine like some of the stuff that I think Max showed earlier on with just like the control volume analysis, that'll get you 90% of the way there. That I would almost worry if you could even trust what the CFD is gonna tell you, just because of the sort of the regimes and really the complexity of the geometry that you're dealing with as well, right? So, but okay, all right, I was just curious.
So it's clear to me that part of this design, that this design is not limited to the belt and wheel itself. You also are designing the upstream.
Yes.
Okay. And that's I think would be an important thing to bring out is that, okay, we also have to create the right situation for what we're sending to the belt and wheel. That's another phase of the design process, basically, and it's not an insignificant.
Yes, absolutely.
One last question. So the rotor and the bucket, it's one thing. Am I understanding that right? Like, will you just 3D print that whole thing in one go? Or
We're planning on fastening buckets so they'd be separate, so it'd be a wheel with holes through it, and the buckets will be fastened.
got it. So have you given it some thought as to like where you could actually make this a fairly open-ended exercise from the standpoint of students could maybe 3D print different bucket shapes
And test it out.
test it out to see, hey, what does the bucket shape do to, say, the power output or the efficiency? And that way, you can sort of muck around with it a little bit that way too.
Yeah, that's a great idea.
Great idea. And I think the reason we had chosen to bolt the buckets on was just the complexity of the geometry would make it easier for 3D printing.
Sure.
But yeah, that's a great point.
I just have a question about your literature. The CFD analysis, did that look at how far that nozzle was placed out from the center of the wheel at all, or?
So this one didn't, but we did look at some of those, and I know the flow will change as it gets farther out and it'll start to fan out more. So typically you want to get the nozzle as close as you can to the buckets.
One of the design things that we noticed a lot in the research was to get the nozzle in the inner radius and not have it just sitting like far out. And that was gonna improve the efficiency a ton, so we were gonna make sure that that is like almost touching, and then you lose less water, and that makes it more efficient. So that's definitely a design process that we're gonna do. We also researched that it was going down instead of horizontal. It was gonna also increase the efficiency that way. So those were both two design aspects that we learned from this patent and other patents that kind of led us to the design we landed on.
All right, no further questions? Oh, yes. Thank you.
Yeah.
Good.
You want to say, I gotta be taking it. Yeah.
Yeah.
Okay. So.
Do either of you want do either of you want to? Maybe.
Yeah, I agree. Let's see what fits. Yeah, you want to leave that, you want to go back.
You can go further out. Keep going. No. Oh, it's me here. We could fit another person over there.
I think it's better. Yeah, I think so.
Yeah, okay.
We're fine.
All right, our last team for the day is the Flying V team with an ultra high bypass turbofan design proposal. Let's get started.
Alrighty, thank you everyone for showing up and coming to listen to our presentation. This is our ultra high bypass turbofan engine design proposal. I am Cadence Ruiz.
Tasmore Dawkins.
I'm Chris Imholt. And I'm Charles Yaden.
And we are the Flying V. So first, a little background on what our problem is and where it comes from. So typically every year, the Institute of Aeronautics and Astronautics, otherwise known as the AIAA, will put out a request for proposal for an engine design for an aircraft for a competition. However, this year, unfortunately, they did not put one out. So we instead used one from 2014 to 2015. And the problem statement from that year was that this project requires an ultra-high bypass ratio turbofan engine for a commercial wide-bodied aircraft capable of supersonic flight speeds that can improve propulsive efficiencies in comparison to a baseline Trent XWB model, thereby decreasing fuel consumption and emissions. So firstly, the big question is, what is a turbofan? A turbofan is a propulsion system for modern commercial airliners. It utilizes a core and bypass flow to generate thrust. So essentially, a large mass of air is brought into the engine, and there is this one fan stage that compresses the flow a little bit and diverts some of it through a bypass nozzle and some of it through the core nozzle, or the core of the engine. And the premise is that by taking a very large mass of flowing air and speeding it up just a little bit, this will produce a lot of thrust, which is why a bypass nozzle is included. And then the rest of the core air is sent through the engine, compressed by compressors, combusted in a combustor, and then sent through a turbine in order to power both the fan and the compressors, and then sent out of a core exhaust nozzle at very high velocities to also produce thrust. So bypass ratio is defined as the mass flow rate of the air through the bypass nozzle over the mass flow rate of the air through the core. And typically a high bypass ratio is defined as any bypass ratio of 5:1 to 12:1. So for our purposes, an ultra high bypass turbofan engine is anything above a ratio of 12:1. So why a turbofan engine? Well, the three main driving factors is the fuel efficiency, the thrust versatility, and then quieter operations. And the fuel efficiency of the turbofan engine is extremely important for commercial airline usage, as the main goal is to keep the price of the seats inside the plane down as much as possible. And this can come about by using a turbofan engine, as the large amounts of mass flow rate around the engine make for less fuel needed in order to get those propulsive thrusts. And while this is relative to other aircraft engine types, such as like a turbojet or a ramjet engine. And then for thrust versatility, it is extremely important for aircrafts to be able to control the thrust for like takeoff and cruise conditions. And so with a turbofan engine and the use of different spools, this can allow for a more tuned thrust throughout. And then quieter operations is an extremely important factor, maybe not specifically to our project, but according to the Federal Aviation Administration, there is codes and standards that talk about not having a certain decibel reading in certain areas, such as like big cities or near airports, in order to keep noise levels for residents as low as possible.
So part of the engineering design process really revolves around the constraints and objectives aspect, specifically from the RFP, the design constraints of thrust, cruise conditions, temperature maximums from the combustor, range, and then nacelle type were specified. But then they also generally specified that they wanted better efficiency and more fuel economy, essentially. Then we took that constraint and we really went through and said, we want to make a strive towards 5% engine mass reduction, decrease the TSFC by 8%, and turbine inlet temperature to achieve those constraints and objectives in a measurable manner.
Okay, so next we'll look at GasTurb, which is the computer software that we're using to model our engines. So it's an industry software that you can study the thermodynamic cycle performance and geometry of gas turbines and other types of engines in areas such as power generation as well. As you can see on the right, there is a few different options of types of engines that you can model in this software. You can do turbojets, turbofans, and ramjets. So specifically, we're looking at a 3-spool turbofan. So in this software, we're able to do parametric studies, which is is varying parameters that your engine is operating on, basically to see how your engine performance changes. Doing off-design studies, which is looking at how the engine operates or performs when you're not operating at your design point. And then thermodynamic cycle design, which is looking at how the air or the temperatures change inside of your engine. And then also looking at internal geometry design, which is like looking at the compressor, for example, how geometry affects the performance of the engine. So in this project, we'll use gas turbine to model our baseline engine. And as mentioned before, the current engine that we're looking at is the Trent XWB, which is the engine used on the Airbus A350. We'll also conduct individual component analysis. So again, looking at each individual component and designing it to best optimize our constraints and objectives. We'll also perform flight mission analysis. So by performing flight mission analysis, we know exactly how the engine will perform during takeoff, cruise, and landing conditions. And then we'll conduct parametric studies to see how each parameter, if it's varied, how does it affect the overall performance of the engine. So on the left at the top, we have the models prescribed in the RFP, which is the Trent XWB engine. So we wanted to recreate this engine in our version of GasTurb and to build some confidence with the software. So by recreating this engine, we know exactly what we're changing and how changing certain parameters then will help us to modify and make the engine better. So on the right is our model that we have recreated. The version that was created in the RFP was in a slightly older version of the GasTurb model. So our length is slightly off, but the thermodynamic performance of the engine is still the same. As you can see, our cruise conditions are within 1% for thermodynamic properties and within 6% for the total engine mass. So next we'll look at the component design. Because of the constraints prescribed by the request for proposal, we did not have to look at an overall engine design. We were more so focused on the individual components that make up the engine. So first we have the diffuser. So diffuser is responsible for slowing down the flow of our engine, or coming into the engine, and also reducing the stagnation pressure losses that happens when you have flight over Mach 1. So we looked at two different designs. So first we had the oblique shock diffuser, which is a oblique geometry at the front of the engine that causes the shocks to be suppressed by allowing them to happen before they get to the of the engine. So first you have this one, which is basically you have one major shock and then two smaller shocks, and then this one is like a series of shocks leading up, and the third one where you have a smaller shock closer to the inlet of the engine. So, and then we have the reverse nozzle diffuser, which is basically you overspeed your engine slightly to move the shock into the actual diffuser where it's weaker and less stagnation pressure losses occur. So when we weighted our diffuser, we looked at the stagnation pressure losses and how the diffuser type is able to reduce those, the velocity reduction, the weight, and the shock suppression. And by doing our component analysis, we devised that the reverse nozzle diffuser is our best option for meeting the standards or the objectives and constraints of our engine.
And then next we took a look at the fan, and for the fan, the main responsibility of the fan is to compress the flow just slightly, as well as send air into the core of the engine as well as around the bypass. And so in this, the main important factor that we found was the weight of the fan itself. And so we looked into different designs with composite materials such as carbon fiber, but also we were looking at work demand as another important factor. And so a couple designs that we looked at was adding gearing to the fan in order to run the turbine spool and the spool of the fan itself at different speeds as to reduce any like stagnation losses due to the fan tips going sonic speeds. And another design we looked at, which is right here on the right, is a double bypass fan, which allows for one bypass flow through a little bit smaller nozzle and then another bypass flow through a larger nozzle to allow for more work output. And with our design choices, we looked at a couple composite designs. One was the composite fan itself, complete composite with carbon fiber blades, as well as just a traditional fan, which had a aluminum copper alloy as the blades. And with our competing designs, we actually found that the traditional fan was better than everything else. And then we looked at the compressor itself, where again, the weight was a very large factor. This is a big component of the engine. And so in doing this, we did another composite material analysis where we looked at just maybe replacing the blades themselves with composite materials, but also maybe replacing the entire compressor itself in whole as a composite material. Another factor that we looked into was the compression ratio, as this is a very important factor, is compressing the flow down to as much as possible before sending it into the combustor will allow for more work to come out in the turbine. And the turbine also drives the compressor itself. So the work demand is an extremely important factor, as allowing for less work to be demanded from the compressor can allow for a smaller turbine stage and overall fit into our envelope, which is we're required to meet a certain diameter and certain length of our engine. And that's also why length is another weight. And so in our compressor analysis, we looked at just traditional compressor, which again had that aluminum copper alloy. But then we also looked at a hybrid material compressor, which focused more on just the blades themselves, changing them to carbon fiber. Then we looked into an all composite compressor, which the entire thing would become carbon fiber. And this would be beneficial, as since it's before the combustor, high temperatures are not too big of an issue. And so material constraints aren't anywhere near as what is later in the engine. And then we looked just into a little side study. So that's what we're able to come up with for
our design, but then also adding more stages than traditional, which would add more length, would allow for less work demand, and overall, we came up with the all composite compressor.
Right, so combustor is the primary mechanism where we turn chemical energy into thermal energy. Specifically, when we look at the combustor, we must now analyze a few different items, specifically the stagnation pressure loss, which is essentially losses from ducting or any combustion inefficiencies you may see. And that's why it's weighted so heavily. Secondly, we put our emissions in there, even though it's not specifically stated in the RFP. It's something that is becoming more of a societal, I guess, mindset and idea that this is important. So we want to also kind of match that idea. And then we also wanted to be mindful of the weight of the component, because even though it's a relatively axially short component, weight is always a factor, especially when you're putting it up 50,000 feet in the sky. So the CAN type of combustor is a type of design that was first introduced, and it is composed of mostly a casing, specifically around an aligner, and then burning within that. And so then it has essentially separate ignition sources within each can. And it is composed of large ducts to each can. The tubo-annular was then next in development, which is a large casing around several concentric liners and their own individual ignition source. And then the most recent modern development is the annular, where it's a concentric ring of casing and liner, and then interconnected ignition. Then you can also technically put them in series with each other or between a turbine, and that would be a sequential burner, where you could actually put different types of fuel in there. So specifically, when we analyzed all of these designs, it came out that the annular burner, which is also the most modern, turned out to be what matched our criteria the best. So again, aforementioned, we had that the turbine drives other machinery. It is the primary mechanism of mechanical energy harvesting, essentially. And so we wanted to look at the max temperature because it's directly outside of the combustor. We need to look at the max work extraction, to drive each component, so fan or compressor. It also, since it's getting blasted by that hot air, you really need to focus on the cooling. By doing that, you can maybe push your that it can see a little bit higher. Again, weight and length need to be considered to help reach the RFP specifications and constraints. So specifically, we looked at 3 types of turbines. A traditional turbine, which would be composed of Inconel or another traditional metal alloy. And it's sized directly to match the machinery it's driving, such as compressor or fan. And then since it's actually composed of Inconel or metal alloy, mindfully, you need to think of creep stress within your analysis. Specifically, creep stress is really just essentially a type of failure that occurs due to elevated temperatures and specifically below what you would expect the yield stress to be for that material. Then the oversized turbine, which is basically copy and paste and scaled to a little bit more work production, capable of allowing more response in such of an emergency or any other time you might need more work. Then we wanted to look at the hybrid material turbine, and this is the most recent in terms of advancement, but it also has some pretty unique production challenges due to the composite natures that it sees. Specifically, you cannot put an all composite system just because of the heat that's coming off of the combustor. But as composites essentially move towards, pushing better materials, that might change. So due to the maturity of those systems, we wanted to actually size directly to our system as it doesn't need additional work. And it's been proven to work time and time again.
So the final design component that was looked at were the bypass and core nozzles. So the biggest factor of the nozzle is the exit velocity because this is what produces the thrust of the engine. Next, the biggest weight was the feasibility of the nozzle designs. So in doing research for the nozzle, different nozzle designs, a lot of them seem to be a little far out of the capabilities of the software that we're using. So we incorporated an aspect of the feasibility of being able to do research and investigations on how these nozzles will affect the engine. We also consider noise reduction as referenced earlier. The Federal Aviation's Administration has standards for noise levels produced by engines. And finally, as per the proposal request, we consider the weight of the nozzle because in order to reduce the weight of the engine. So here are some of the nozzle designs that we looked at. So first is a typical unmixed nozzle along with a mixed nozzle. And the concept of a mixed nozzle is essentially taking the outer casing of the engine and extending it past the outlet of the core in order to give the bypass flow and the core flow a space to mix before being sent out of the nozzle and producing thrust. Additionally, there is a chevron nozzle design, which the idea here is the trailing edge of the nozzle is essentially formed into a sawtooth pattern. So the flow of the exhaust will concentrate at the tips of the teeth on the trailing edge to allow mixing between the bypass flows and the core flows in order to reduce noise. Additionally, in the middle, there is a passively controlled nozzle design. This one is essentially a liner on the nozzle, and the whole premise is it's similar to when you take like a glass bottle and you blow over it and it produces noise at a certain frequency. It's essentially the same premise, but in reverse, where as the flow flows over it, it will absorb certain frequencies and reduce the noise production of the exhaust. And finally, as discussed earlier, we looked at a double bypass turbofan. So as it's included in the fan, it also has to be included in the nozzles. And in comparing all these design choices, we found that the chevron nozzle design choice was best suited for our applications. And so overall, for the proposed design is the reverse nozzle diffuser, as it is the most effective at decreasing the flow velocity with minimal stagnation pressure losses. And I know earlier it was mentioned that the fan we chose was a traditional, but the fan is a very integral part of a turbofan engine. It is essentially what defines the turbofan. So it has been a very intense discussion and all the way through this presentation. So there was a bit of an error that wasn't caught, but we will be using a composite fan and compressor in order to reduce the weight. We will be using an annular combustor in order to reduce the weight with minimal stagnation pressure losses. We will be using a traditional turbine as it is the most effective at powering the fan and compressors. And as previously said, we will be using a chevron nozzle as it reduces the exhaust noise with minimal effects on performance.
And then for future work, since this is an AIAA competition, since the competition got scrapped, we are now going to the Region 3 conference in Akron, Ohio in the beginning of April. And so a couple deadlines that we would like to make is our abstract deadline. So that's when we have to submit our abstract for the conference. And then we're looking at making the paper itself to meet that deadline. And then the conference itself, as I said, is in the beginning of April. And from there, we'd really like to have the bulk of our engine made, and we can receive any peer review revisions from industry experts. And from there, we can revise our engine down and make our final paper and submit for the end of the semester. And so
we have a special acknowledgement page because we would like to thank Dr. Ian Hallowell, who we've been working closely with throughout the semester through multiple consultations with him. And then also he is actually the RFP writer for AIAA. And then additionally, we'd like to thank the MSOE department faculty of the mechanical engineering department, specifically because of their education that they've continued to provide and the support that they've continued to give. So thank you.
Questions? None?
You guys focus a lot on performance. Have you guys done anything like, is cost considered into any of this? Or is it just like, can I get the best engine? Like, you're gonna pay a lot for those components, you know?
So the cost benefit really comes back to the efficiency. As mentioned before, you want, as an airline, you don't want to make your cost too high. So by using less fuel, which is the most expensive part of operating for this engine, you want to minimize how much fuel you're using, and that will reflect how much like your costs will be driven down.
What temperature range are you talking?
So, currently, we're looking at about 3,200 Rankine, which is about 1785 Kelvin. And through some research that we plan on doing later next semester, we would like to increase that temperature range in the turbine through the use of CMC materials such as like silicone.
Yeah, silicon carbon.
Yeah.
And on those composite that you talked about, mostly you talked about basically the carbon composite. Have you looked at other using, say, metal matrix composites and other things that are in the process?
We have.
Did you come across those?
We have come across them, but the papers that we've like essentially put in our literature analysis haven't been able to release the specific numbers related to those, so it's hard to vet that information.
And you also said building in a, are you physically they're gonna build this thing or?
No, this is,
No.
it was make us in, build the full model.
Yeah.
Of the system.
That makes a lot of sense.
What's the temperature at the end of compressor?
I believe it was about 900 Kelvin. So I don't think it was high enough to have any effect on like carbon fiber materials through the research that we did.
So up to what temperature can carbon fiber materials continue without degrading?
I believe I found some research and I think it was about 1300 Kelvin. But I don't have a set number right now. I just believe that was the range that it was at.
Thanks.
So you're going to use that software to evaluate the performance once you get that done. So it seems to me in my simple mind that there's two parts to this. There's the design and the performance aspect of it, and then there's the materials aspect. Is that fair?
Yes.
Okay. And those have to sort of go together. You do the performance, you're going to get a sense for temperatures and those sorts of things, and then that goes into the, okay. And you will, in the end, you're going to specify materials all the way throughout. You're going to predict performance throughout.
Yes. Well, that kind of goes back to the uncertainty of the materials in the sense that, as mentioned before, with like CMC materials, a company's not going to tell you exactly what components they use to make their CMC. So it is not so much as saying we're going to use X. We're basically going to provide like estimates based on what we expect future advancements to bring for the engine.
You're considering using hybrid metal, non-metal?
Yes.
Okay, what is that, again, for the not very educated person, me? What does that interface look like between metal and non-metal?
So
Are there issues with mating those?
the composite materials and the metal materials they're not directly in one part mated together. They are more of like, so like for the compressor blades themselves, they actually like mated into like a big hub. And so the carbon fiber material isn't also metal material, it's just carbon fiber. And then like the hub of the compressor would be like a metal material. So we would make them.
So this is an attachment.
Yes.
What would that attachment be like?
I might usually go back to so as you can see down here, there's a Christmas tree.
Yeah.
Basically, and so this Christmas tree is then slid into a slot in the hub itself here. And so that's how those two are mated there.
Okay. Interesting. All right, that answers that question.
How much of power that would be generated by turbine would be, or how much of power is derived by the turbine and how much is left for thrust? Any particular numbers like ratio, like, okay, 50% would be left for getting thrust and remaining would be diverted to compressor and other auxiliaries
Okay.
that are needed. Is that like part of the constraint or is that something you have to set?
No, I don't believe.
So what are you setting?
So we're gonna set the compressor and then size the turbine. So if you can set the compressor, since it has to match by essentially the work, the mass flow, and then also the RPM, then you can set the turbine and that ratio would be further defined.
But what about auxiliaries?
So
Like you need like to circulate oil and so forth.
yeah, the model doesn't specify any of that additional like criteria. You can take power off as like a bulk number essentially, but also in the RFP, they do not specify that. So it's best to probably leave some margin there.
But then you're competing with Trend, right? And Trend does have that auxiliaries taken. So do you know the numbers that Trend takes away from auxiliaries?
So a lot of the research that we actually did on the Trent engine, it was really rough in terms of like Rolls-Royce really didn't want to give up a ton of information about the engine specifics, the numbers. And so a lot of it was qualitative. And so we were just trying to pull as much information off the RFP itself. And so the information we were kind of provided in the RFP was, for the most part, all the quantitative numbers that we were able to get. And so that's a great point. We can look more into it next semester. However, we weren't able to find any numbers on that through our research.
What would be typical number for a typical turbofan?
In terms of like driving the auxiliaries?
Yeah, what percentage of power is diverted to auxiliaries?
Would believe it's less than about 5%. Not, because I mean, a majority of the work is going into the compressing the flow through the fan and compressor, and those are very large components, whereas the auxiliaries are much smaller. So I believe that it would be about 5%.
Okay. Any other questions?
I got one. You mentioned, I might have just misheard you or just didn't understand what you were saying, but you said that the double bypass increases work, and you mean like work as in like in terms of thrust, or what do you mean by it?
Work demand. I mean, put another fan on there, you're essentially doubling the work demand from the turbine.
Yeah. The benefits of it would be that probably increased, but through our research, we couldn't find anything that would like make it advantageous to use that.
All right, round of applause for Cooper.
Come on, Dr. B, the semester's over. It's almost over. That's King Kevin to be kind. I know. Back to the. Yeah, we have to rank each.
Oh, thank you.
That's not fair. Well, we don't have to rank ourselves, so I guess it's. Yes, that's right. Everyone's. You rate yourself, you rate each other. Et cetera, et cetera.
I'm going to have yours.
Yeah, I'm gonna put yours in your mailbox by Monday at the latest.
Yeah, thank you.
Yeah.
Dr. B, do you have a header?
I can get mine to.
Oh my God. Here, actually, I'm reading. My actual book back. I didn't want to walk away. So I can't wait to see it in the flash. In the flash. Don't worry, don't worry. I'm gonna be at the flash right there.
No, the one that you made was real big. The one that you forged, past it.
Yeah, you want to see us in the.
That's right. It's just illegible. That's right. See you guys later.
No, I just saw that.
Oh, well, that's, it's. Yeah, it's not a requirement.
It's really. Thanks for taking that.
Sure.
Yeah, Taz, you really forgot those agendas, Taz.
Yeah.
What's the deal with that?
Oh, that was good, that was fun.
Good to hear.
It's like. That was interesting. Yeah, that was good.
Yeah, it's in value. I think it's pretty good.
Oh, man, that is a lot of stuff.
Can you imagine if I just write over all this? The same thing. It's like you guys have this.
Yeah, I'm going back to. How are you doing? You're gonna go. I have to pace myself, but I'm okay. I've got.
Yeah, but.
Yeah, I'm going to the problems, but all that is doable.
Yeah.
Sunday night, so.
That's my goal.
Yeah.
Or they're just spelling something else for me.
Oh,
yeah.
Another rapper?
Something like that.
Yeah, it's a semester rapper.
So do they evaluate themselves?
Yeah, we'll let you come back.
Well, I mean, they evaluate themselves, but I was like, that's not fair to the cat. Because we're told there's all. It's not good to evaluate yourself. I was practicing.
Literally, I have the same thoughts for everybody.
Right, that's why I'm kind of just about to start drawing arrows everywhere, because I have the same feedback for everyone. I think we all contributed to
I have a question. I'm available between 8 and 10. Someone else said there, I got 10, this, but like, can we just say there? I can do what on that, all the section.
I mean, if you honestly believe.
I should have said that,
then you're welcome to do it. Like,
I honestly think that.
Yeah.
For sure. No, I mean, I'm not twisting your arm anyway, right? It's just, it's a useful way to.
That's pretty much. It's
You gotta see how you stack up, how you see yourself and how you see. That's your colleagues, you know. And I'm not gonna show the stuff to each of you, right? Like if so if you decide to look back on somebody, I'm not gonna be like, oh, maybe I should check out.
I'm actually gonna put you down as a teammate, and I'm only gonna.
I have a feeling.
Yeah, you guys do it, count you as a teammate.
To be honest, you've already had the opportunity by filling out the evaluation.
Right.
No, they have it now for Dr. Hart. Dr. Hart had a separate section.
Yeah, they both have separate sections.
So you had your opportunity.
Yeah.
Hope you used it well.
I did.
Awesome.
Short breaks. I would hope that you would know us well, that you've seen our projects plenty of times now, that you know that none of us, it's fine. Like to skip out against the player.
Right, yeah, I think we're all pretty reasonable people here.
They were like highlighting the cars around the family.
You'd be surprised, there've been some years that I've had where
mistakes. Remarks highlighted around like.
Yeah.
Ball. Yeah, traditionally.
They were kicking off.
Yeah, so it's traditional.
Was it for this?
I only do.
Yeah, right.
These sort of.
That makes sense.
Like I got it just, gut feeling, and then I looked at the evaluation for everybody, it's just like, this person did nothing on the entire semester, or the entire quarter.
Yeah, I've heard some shit about that. What if this one bit can happen? People will straight up not do worse. Oh, there's more. Oh my god. Like, I'm gonna hit super well with you.
Dave can put in his hair, get it off. And that's my explanation. There we go. In the space.
No, it's about Roger, he gives $300 to Miami.
That's an involved.
Yes.
Hell no.
Again.
I will add one, I will one
How do I do that? This is great. If I wanted to say.
It's 25 points. Yeah,
Okay.
I'm gonna give myself 26 and all of you 24 and 3/4.
Okay.
Wouldn't it be 24 and third?
It's
Somebody
goes 2/3.
No, wouldn't it be one?
Oh, that's fine.
No, because you're taking 2/3 from each person, that's 2 actions.
But if you had 26, and then there's 3 of us.
Wait, you're in the last thing to
That would be 74,
Just like.
so 74 divided by 3.
Okay, okay. 74 divided by 3 is, well, 72 is, 72 divided by 3 is 24.
24
That's.
So,
I wrote what I.
no, it's 24.6 repeating, because there's 2 left over.
That's right. He is right. Cadence is right.
I used to do math competitively in middle school and high school.
This is evil. I'm not like that. That's
Just assign everyone 25 points.
No, it's just like assign the top member. Jesus Christ, this isn't talking about world or whatever.
Oh, shoot.
I should give you more points for that save.
We're showing up late and.
Was that late? We were supposed to.
No, no, no.
We're down.
At the
Practice.
practice.
Oh, yeah.
Me and Link at the practice.
Yeah. Any thoughts on our presentation? Okay.
It was good. And I think hopefully, there's some good things that came out of some of the questions. Yeah, things to kind of think about.
Questions like immediately.
Yeah, I was like that. I think that's a pretty good sign.
Like, they had to dig in, kind of.
Yeah.
You're good.
I was extremely confused at first when Dr. Baez asked the question, that percentage of the power is going to thrust, and I like did not know how.
Yeah, I mean, the simple answer is none.
Yeah.
Because there's no power left over.
Yeah,
right?
yeah.
So I think the framing is more like how much energy should be left over in the flow. It's not a work power related issue.
Yeah.
So,
It's gonna step in and say that I was like, and say like, technically, like, you know, like, you just wait for my to color your machine.
That's it.
That's like, I was like, yeah.
That's what
Yeah.
This stuff.
And I did also mention that the outtake, the power outtake is also mentioned in the art. But you don't say it, it's just that it's used to see, I think.
But that's really not much if you think about that. That's.
Chris, you can do the math.
It's like
You
really.
have the
That's fine.
thing for the.
You could just raise it back.
Oh, yeah, there's one on the way back. My bad.
Forward.
Conclusion.
It's just to say, would you work with these people or not?
Yes.
Yeah.
Yeah, yeah, I would, for sure.
Yeah, man, I'm sorry.
This is, Charlie's.
Oh, yes. I've lost so many of these.
Really?
Yeah, man, especially the USB,
Oh, I bet.
I have like 4 sitting in my drawer without a USB.
Oh,
Geez, so.
I don't know why I came all the way out here. I could have just reached over the tapes. Now I gotta go grab my stuff.
Thank you. Thank you guys, thank you.
Yeah.
Thank you.
I can't believe you guys
That's fine,
signed that.
everyone.
You signed it before the.